We have an infinite solenoid, but the current that passes over the solenoid changes with time. So that means that the magnetic field that solenoid produces also changes with time, which implies that there is an induced electric field around, and we would like to find the induced electric field. But in this problem there is symmetry, so there is cylindrical symmetry, so that's crucial. Without the symmetry we cannot say much about the electric field at this level. So as a result we are going to use this. So A is the radius of the solenoid, and so the other parameters are basically the number of turns of the solenoid, which is what we use for computing the magnetic field. And I'm just going to show the rate of change of the current by di over dt, but I'm not going to insert any numerical values. So it doesn't matter whether this is increasing with a steady rate or decreasing or whatever. So I'm just going to write down an expression which is valid for all possible situations. So let's remember this, that for a solenoid, the magnetic field produced is produced inside. There will be a magnetic field inside only, and we have called this as the inside magnetic field. So the outside magnetic field would be 0, and the inside magnetic field has the magnitude given by mu0 n times I. This is by using Ampere's law. We have seen that we can actually compute this, and this is a result that's independent of the shape of the cross-section of the solenoid. But in any case, this is one of the things that we are going to use. So in this case, since the current changes with time, the magnetic field also changes with time, and so as a result, this causes an induced electric field. So I'm going to look at this problem from this top view. So from this view, things are going to look like that. So this is the solenoid, the wire part of the solenoid. So there's actually a current flowing in there. Because of the existence of the current, there is an induced, there's an there's a magnetic field inside, so that's the magnetic field inside. In means inside. There's no magnetic field outside. This is from the previous chapter. By using Ampere's law, we can deduce this. Just remember that. This picture has rotational symmetry, cylindrical symmetry. So therefore we say that at any point in here, let's say at this point, the electric field should be along this direction or opposite to that, depending on whether the current is increasing or decreasing. So we can also decide on that direction too. And we would like to compute as a function of the distance from the symmetry axis. I would like to compute the induced electric field. And there are two situations actually. There are two special cases that we can consider for a point inside or for a point outside. So A is the radius of the solenoid. My point, is it inside or outside? So I'm just going to start with the inside case. So let me erase all the unnecessary details. So let's remember all the details in here. All right. Let me show the axis by this point. The axis by this point. I would like to compute the electric field at this point where that distance is r. So I'm interested in the value of the electric field at that point. That's the induced electric field. I can, to be able to find this, I just imagine, so let me draw an imagined curve in here. I just imagine some kind of a loop in here. This is not physical, this is just imagined. But I can also imagine that I can place a wire in there. But without the wire, I can also talk about the EMF. So there's some kind of a loop in here. So I'm just going to add in there that this is imagined loop. imagined loop. I'm also going to talk about the EMF on that loop. So I can compute this EMF in two different ways. I can, by using Faraday's law, I can compute the flux passing through the enclosed surface enclosed by that loop. Or I can use the line integral of the induced electric field. This is basically, there are these two alternative ways. One alternative way involves the use of the electric field, which is the one that we would like to compute. So as a result, what we do is we just express this line integral of the electric field to the Faraday's law expression. Since I can compute the right-hand side easily, I can also compute the left-hand side easily. By the way, in a lot of different contexts, this equation might also be called as the Faraday's law. In any case, of course, when I ask you what the Faraday's law is, probably you should actually say that it is that relationship between the EMF and the flux change, right? So in this case, because of the symmetry properties, I can express this line integral as the magnitude of the induced electric field multiplied with the circumference. For the case of flux, we have this. It is the magnetic field multiplied with pi r squared. So as a result, this is the rate of change of the magnetic field. But the magnetic field is, I know that for a solenoid is equal to mu0 Ni. So therefore, I can express this part as minus mu0 n pi r squared di over dt. So pi's cancel, one of the r's cancel. So therefore we find the induced electric field to be equal to minus mu0 n divided by 2 di over dt multiplied with r. All right, so this coefficient, you can think of it as a constant that doesn't depend on where you choose your point. So from here, you can see that I'm going to discuss this on the diagram. So as a result, let me erase everything in here. So it basically tells you first that the induced electric field at the axis is 0. And this induced electric field increases linearly in magnitude as you go away from the axis. So as a result, at these 5 special points, the induced electric field would be like that. At this point, it would be like that, and so on. So as a result, as you go away from the central axis, the induced electric field increases from 0 and it reaches to its maximum value right at the edge of the solenoid. All right, so we can then continue for the next case. So this is the case where the point in question is outside. Let me draw the current in here. The point in question is outside the solenoid. So there's an induced electric field also in here. And to find this, we again draw this imagined curve. But in that case, we just notice that the magnetic field is not everywhere. It's only inside the solenoid part, which has a radius of A. Okay. So again, I'm going to use this expression, that the EMF is expression. So as a result, the induced electric field dotted with dl integral is equal to minus the rate of change of the flux. So this part is again the same, at least in terms of the unknown electric field, it is the same. But the flux integral, magnetic field multiplied with the area, but the magnetic field is only present in this area inside the solenoid. So there is no magnetic field in here. So that means that I have to multiply the magnetic field with the area of the solenoid in here. All right, so that's the crucial difference between inside and outside. It is that part. So in the previous case, the area was the whole area of this imagined loop, or the surface enclosed by that imagined loop. So in our case, of course, the imagined loop encloses a bigger surface with area pi r squared, but only in a smaller part of that surface there is magnetic field. So therefore, I write down the area of the region in here, which contains the magnetic field. So that's the only difference. As a result, we can do the calculation again. So that's mu 0 n di over dt pi times a squared. So induced electric field is therefore equal to minus mu 0 n divided by 2 di over dt a squared divided by r. So as a result, at our side points, you can say that the electric field is largest in here at the edge of the solenoid, and as you go away from the solenoid, it just decreases like 1 over r. Right, probably I didn't draw this in a scale, but of course if you plot this curve, you're going to get 1 over r. Or if you want, we can also draw this as a curve of induced electric field as a function of r. So there's this special radius value in here. It's the radius of the solenoid. So inside the solenoid, sorry about that. Inside the solenoid, the induced electric field increases linearly. It just starts from 0 value at the axis, and then it reaches the maximum value at the edge of the solenoid. So outside, it just decreases like 1 over r. So outside, it has a 1 over r behavior. Inside, it is r. Again, let's remember that this is the non-conservative electric field. So therefore, we cannot define a potential for this electric field.